Hi, in this video we're going to work on some central measures like mean and some dispersion measures like standard deviation and variance, both in the context of data, so you could say statistics, and in the context of probability theory, because in both these situations these measures are defined and they're actually closely related, which I would like to highlight by this setup of doing things here on the left and on the right sort of simultaneously. So let's start with an experiment. You throw a die multiple times, to be precise 12 times, so you write that usually with an n. N is 12, and this will generate some data, a list of outcomes, 2, 4, and whatever other numbers all the way up to 2, once for the last. And well, in statistics we order this data, and one of the first things you do is you order according to outcome. So there are 6 possible outcomes, and I put a table here just putting the frequency for each outcome, and if I'm correct these numbers add up to 12. And then a central ingredient for our computations later, and also the connection to probability, is made through relative frequencies, which means you divide the frequency by n. So in this case it will be 2 over 12 is 1 over 6. This is 1 over 12. This is 3 over 12 is 1 over 4. 1 over 3, 0, and 1 over 6. And if I've done it correctly again, this added up to 12, this adds up to 12 over 12 is 1. So the sum of all the relative frequencies should be 1. Okay, and the relation to the probability theory is as follows. There you investigate a random variable, that is a variable whose outcome depends on a probability experiment. It's clear that the experiment is here again to throw a die, and the variable is the outcome of the throw. There are 6 possible outcomes, and here are the probabilities. And this is an idealized case. We model the die by a perfect cube, and we expect every side to come up with equal probability, so 1/6 for each of them. And of course what we would, there are theorems about this that say that if you repeat the experiment often enough, in some way these relative frequencies approximate these probabilities. If it's a perfect, the more perfect the die is, the better this correspondence is. And well, now we go to central measures. Central measures are ways to say something here about the data, here about the probability distribution in one number. And of course, you're very well acquainted with the notion of mean, and you're used probably to compute this directly from the data as 1 over, so the mean is denoted by maybe in this case S bar, and you compute it by 1 over n times the sum of all the data Si, where I goes from 1 to n. So that's in this case 1 over 12 times 2 plus 4 plus all these outcomes, and the last one was, I didn't put the last one, but let's say it was 2 again. And then there must be some outcome, which I've got over here. It's 11 over 4. Excellent. But there's yet another way to do this computation using only the relative frequencies. And that's as follows. You take the sum again over I, but this time it runs from 1 to k, where k is the number of outcomes. So k is 6. So I've got 6 different outcomes. They happen to be the numbers 1 to 6. So then we multiply the relative frequency fi times the actual outcome xi. So in this case, this would be 1/6 times 1 plus 1/12 times 2, etc., all the way up to over 6 times 6 again. And of course the outcome should be exactly the same, 11 over 4. Not going to check, but you can do that of course. Now let's see. As you can see, there's also this central measure which is defined in the case of probability theory, and it's called expectation. Now of course there's not an obvious mean here, but the interpretation of the expectation is that we're going to compute something of which we expect that if you repeat this experiment often enough, the mean is going to approximate this expectation. And since, of course, these relative frequencies are going to approximate these probabilities, the expectation should then be defined as, inspired on this second computation, as the sum of the probabilities times the outcomes. And here again, I runs from 1 to k, where k is the number of possible outcomes. And in this case, it's 1 over 6 times 1 plus 1 over 6 times 2, all the way up to 1 over 6 times 6. And the outcome in this case is, I think, 3.5. So it's 7 over 2. So 11 over 4, 7 over 2, well, 14 over 4 would be the same. So you see that this is not yet very close to this, but with higher frequencies here, more repetitions, it should approximate this number. Okay, so this is the central measure as it is for in statistics and in probability theory. Now there are also dispersion measures. These are measures that tell you something about how the data is distributed. The mean just tells you around which number it more or less is distributed. The variance and other dispersion measures tell you about how it's spread. Well, how do you compute it? It's actually the same in a sense for both cases. You're interested in at first at the deviation from the central measure, which in this case is the mean. So we're going to look at how each of the possible outcomes, and you can define it in two ways actually. First, in the case of just all the data here, so then you can look at a possible outcome Si, and then you look at the difference with respect to the mean, which I denoted it by S bar. So minus S bar. And since this can be positive or negative, and you don't want things to cancel out, it is the way things go that you square this thing. And now all these squared deviations of this, you want to take the mean. So it's sort of the mean quadratic deviation with respect to the mean. So we're going to sum over all data. In this case, it's I is 1 up to n. And then we divide by n because we want the mean. So this is the variance on the one hand, the variance of S. And like before, there's yet another way to do, since we calculate the mean and we can compute the mean also in this way. So what you can also do is you sum over all possible outcomes. So I is 1 up to k. And then you compute the deviation, which will be the same for each, if the outcomes are the same. So in this case, I can take xi and then deviation of with respect to s and square it. And now we just multiply with the frequency. And this should give you the same outcome. So if you want to compute this, and you do it by hand, which I do not advise, you have computers for this or maybe a calculator, but just to show you once we are going to do it, you can do in steps. So maybe at first you want to compute all these deviations of, we're going to use the second version of xi minus S bar. So S bar was 11 over 4. So just to make my life easy, I'm going to take my previous calculation and use it. So we're going to have some negative numbers at first, I think, because so this is minus 7 over 4 for the first one, right? This is outcome 1 minus 11 over 4 is minus 7 over 4. And then it just increases by steps of 1. So it's minus 3 over 4, 1 over 4, 5 over 4, 9 over 4, and 13 over 4. Okay, so far so good. Then I can compute the squares of all this. And well, let's have some fun here. This is 49 over 16. This is 9 over 16. This is 1 over 16. This is 25 over 16. 81 over 16 and 169 over 16. And now the variance in this case should be the mean of all these squares. And so we compute it using this formula. So the frequencies, which is for the first one, relative frequency was 1 over 6 times 49 over 16 plus etc. That's right, the last one, which was also 1 over 6 times 169 over 16. And well, you can approximate this, and it turns out to be about 2,85. Okay, great. So this is the variance, and it gives you an idea of how the data is spread out. And actually for, now you can sort of guess how it should be defined in case of a probability distribution, because we take this second formula and we replace the relative frequency by the probability. So you get variance of this random variable x equals the sum of i's n to k, or number of outcomes, and then you get pi times, and now watch out, because we can't use s, which should be s bar really. We have to write expectation, right? So it is times the outcome minus the expectation of x squared. So this is really the expectation of this deviation squared. And yeah, if you want to compute this, which you do, there's again work to be done. So you follow the same strategy, I think. If you do this by hand, you do it in a few steps. So you first start looking at the outcomes minus the expectations. So let me get my paper just to make sure I don't make any mistakes. It starts off with minus 5 over 2, and then 3 over 2, minus 3 over 2, minus 1 half, half, 3 over 2, and 5 over 2. Maybe I could have done that by heart. And then you square them. It's 25 over 4, 9 over 4. There's 1 over 4, 1 over 4, 9 over 4, and 25 over 4. And maybe this I could even compute by heart. If you sum all this, it's 70 over 4, isn't it? 70 over 4. But anyway, let's do the computation. So the variation of x is the sum. No, let's not write the sum. We're just going to do it, right? It's 1 over 6 times 25 over 4 plus all the other ones plus 1 over 6 times 25 over 4 and everything in between. And you can see it's each time it's 1/6. So actually it should be 1 over 6 times, what did I just say? 70 over 4. Okay, so well, you compute this and it turns out to be more or less 2,92. And this is really nice because it's pretty close to the variance here. And so that's of course again what you expect. If the frequencies here would be higher, you would repeat it more often. This variance is going to approximate the variance of your model, which is the whole idea of a model that is sort of predictive. And now there's one other dispersion measure that I'd like to measure, which is more common or used for measuring the dispersion, and that's the standard deviation, and it's nothing more than the square root of the variance of S. There you go. So I can compute it for you here. It is more or less 1,69, and it's defined exactly the same way here. The standard deviation of this random variable is the square root of the variation of the random variable, and in this case you take the square root of that number, and it's approximately 1,71. So there you go. It's been a bit of a long video, but now you've got a nice introduction of these central and dispersion measures, both in the case of probability theory and of statistics, and hopefully you also see the connection. So thanks for watching.